Good afternoon, everybody. Am I audible? And to the participant to unmute themselves.
Kindly, please permit me to share the screen.
Just a minute. Okay, sir. You may share now.
Okay. Okay. You want to say something? Then I'll share once you are done with this screen.
No, nothing, sir. I have make you and co-host, so you may share now your screen and anything. Wait a minute. For introduction, and then we will allow you for sharing your screen, sir. Thank you. Dr. Vishwesh Badheka, sir. Am I audible to you, sir?
Yeah, you are audible. Shall I share my screen?
Hello.
Can you hear me?
Just a minute, sir. Hello. Am I audible, sir, now?
Yes, yes, you are audible. Yeah. Can you see the screen? Is the screen visible? Can you see the screen?
Good afternoon, everybody. Now we'll start the second session. FD conversation is on topic friction stir processing for surface composites and super plasticity, which will be delivered by Dr. Vishwesh Badheka, sir. On behalf of Tape Diploma Engineering College, we welcome Dr. Vishwesh Badheka, sir, in 5 days online faculty development program. Before starting the session, I would like to give brief introduction about him. Dr. Vishwesh Badheka, sir, studied metallurgy at MS University of Baroda, received bachelor's, master's and PhD in metallurgical engineering. Presently, he is working as head of mechanical engineering at School of Technology, Pandit Deen Dayal Petroleum University, PDPU, Gandhinagar. He has received funding from various funding agencies, including DST, ISRO, DRDO, and DAE, for his research in the area of advanced welding processes. He also has published 60 international journals, publications, and 70 international and national conferences. He has 2 Indian patents in the narrow gap welding torch and torch oscillation device to his credit. We are grateful to have such a decorated personality between us. Now I request Dr. Vishwesh Badheka, sir, to start the session.
Okay, so good afternoon, everyone. Kindly please confirm whether my voice is audible to everyone. Is it audible?
Yes, sir.
Okay, and the screen is visible. Can you see the screen? Hello.
Yes, sir. Screen is visible, sir.
Okay, okay, fine, fine. So once again, good afternoon, everyone, and welcome to this second session of this particular faculty development program. I would like to thank the organizer for giving this opportunity to share the development in the area of friction stir processing. So let me begin the talk. So these are some of the key research areas in which we are working. So one of the key research area is friction stir processing, which would be discussed today. In addition to that, there are other key areas in which we are working. One is on activated TIG welding process, metal, narrow gap welding, friction surfacing, wire arc additive manufacturing, friction stir additive manufacturing, application of solid wire and metal coated wire in the narrow groove conditions, friction welding. And this is a beautiful photograph of friction stir welding as well. So let's begin the session. So content of this presentation is like this, because to understand the friction stir processing, we need to understand the friction stir welding. And to understand the friction stir welding, we would be discussing friction welding as well. Then we would be discussing some of the process variant. And there are many variants that FSP has. And we would be discussing today two major variants, FSP for surface composite and FSP for superplasticity. And please feel free to interact during the session. If you have any specific question, keep a note of your questions as well, because there is a recording going on. So we need to handle the questions at the end. So let us understand and differentiate, because when you look at the welding processes are mainly classified in the two categories. One is the fusion welding, another one is the solid state welding. So when you say fusion welding, the fusion means there is a melting phenomena, and that's the reason. Whenever there is a melting phenomena, you melt the metal, you melt the filler metal also, and because of melting, the molten metal has the tendency to react with the atmospheric oxygen in case of shielding is not proper. So you may get oxidation also. You may get porosity also in the weld metal. Sometimes you may get microsegregation and hot cracking. These are the common issues you have in the fusion welding, right? Why you have these issues? Because there is a melting and solidification. I'm sure you all know that welding is also termed as localized casting. Why the welding is termed as localized casting? Because you are all familiar with the casting operation, right? So what do you do in the casting? You pour the molten metal into the mold cavity, and then the molten metal gets solidified. Now you are doing that in casting, but in welding, you are doing that melting and solidification only wherever there is a joint edges are there. And that's the reason it is called localized casting, because you are doing that melting and solidification only at the local level, only at that particular edges, joint edges, right? Now, when you compare fusion welding with the solid state welding process, you are well below the melting point of the metal. In the previous speaker, he talked about many fusion welding processes, right? So we would be discussing mainly the solid state welding processes, and that too, friction welding, friction stir welding, and its variant called friction stir processing as well. So in solid state welding, you are well below the melting point of that metal. Say for example, if I'm doing a friction stir welding or a friction welding of aluminum, right? Aluminum melts normally at 660 degrees centigrade. So you are below the melting point of that metal. While in the fusion welding, you need to melt the metal, right? So since you are not melting the metal, the defects which has been referred here, in fusion welding, there are certain defects which has been referred. So those defects can be reduced to a certain extent because of the solid state nature of the process. And another important benefit of the fusion welding is, the dissimilar combination. Dissimilar combination means what? Now industries, they are looking for dissimilar combinations like aluminum to steel, aluminum to copper, magnesium to steel. All those dissimilar combinations can be welded very easily with the solid state welding processes. They are very much challenging with the fusion welding processes, right? Why there is a challenge with the fusion welding? Because you need to understand the metallurgy. You need to understand whether they are metallurgically soluble in each other or not. You need to look at their metallurgical properties also. Okay, so whether they are metallurgically soluble in each other or not. At the same time, you need to look at their thermal properties and the mechanical properties also, right? And that's the reason. Say, for example, if there is a large difference in the mechanical and thermal property, there is a lot of challenge in joining those dissimilar combinations. And that's the reason the solid state welding process is being more preferred for the dissimilar metal joints. As I gave you the example of aluminum to steel, which has been widely used in the automobile application to reduce the weight of the vehicle, right? At the same time, you see the another fourth important fundamental difference is the alloying element. Now you see that when you melt the metal, there is a mixing. There is a mixing between the filler metal and the base metal at the atomic level, because the molten metal is there, and because of that, the mixing between the filler and the base metal at the atomic level. While in the second case, solid state welding processes, right, you are joining them, right, not through the liquid route. You are joining them with the mechanical alloying, right? So there is no true solid solutions, right? And this is what the another metallurgical difference between the solid state welding processes and the fusion welding processes. So after giving you this fundamental difference, I'm sure that you all know what are the welding processes which comes under the fusion welding. Say for example, your all arc welding processes, right? Your resistance welding processes, your lean welding processes, right? Gas welding processes, they comes under the category of fusion welding. While solid state welding processes, friction welding, friction stir welding, ultrasonic welding, explosive welding, diffusion welding, right? All those welding comes under the category of solid state welding. So let us look at the small clip here, which probably help you to understand the process. Now you see here, there is a lathe machine here, and you know there are two components which are rubbing against each other. Now you see, right? And then when you hold that situation, right, because of that, there is a friction heat, and friction leads to the development of the heat. And because of that, you know, material become red hot at the interface, and then you apply extra force, right? So this process is called friction welding, right? And from this process only, the new process which is called friction stir welding has been derived. So this can be easily demonstrated to the undergrad students on a lathe machine, right? So let us understand. There is another variant which is called, which has been derived from this particular process, which is called friction stir welding. Now you see there is a process called friction stir welding. How the friction stir welding works and how it is different compared to the friction welding, right? So friction stir welding, why we are discussing friction stir welding? Because friction stir processing has been derived from friction stir welding only. So what is friction stir welding? You see here, you require a special tool. Can you see there is a tool here, right? And this tool has a special features. You see there is a pin, there is a shoulder. So this, whatever the pin you have, right? That pin has certain features also, like you have a threads, you have a cylindrical pin, you have a conical pin, right? Sometimes you have a hexagon also, pentagon also, right? Those pin shapes. So there are various pin shapes are possible. In addition to that, there is another important feature, which is the shoulder. So there is a pin, there is a shoulder, right? So what happened during the process? During the process, FSW is nothing but you have a, you know, you require, this is a tool, and the tool is initially penetrated in the during the welding, and then, you know, it will stir and mix the material. Let me show you a small clip here. Now you see here there is a entire process diagram which is being given to you for a better understanding. You see there is a tool. Now you have the pin and the shoulder play a very important role, right? They are like in friction stir welding, the tool is the heart of the process. So you require the tool. That tool will initially start at certain RPM, then it will move towards the joint area, right? You see there is a down arrow which indicates that the tool is moving towards a down. So that particular stage is being called plunging stage. Once the plunging has been done, the shoulder makes the contact with the top surface, right? And because you see the shoulder diameter is more than the pin diameter, right? Shoulder diameter is, say for example, if it is pin diameter is, say for example, is 6 millimeter, the shoulder diameter is around 18 millimeter. So 3 times. You see there is a pin here. If the pin diameter, you go with the maximum diameter, the maximum diameter is 6 millimeter, the shoulder will be around 3 times, 18 millimeter. Because of large contact area, you see a lot of friction heat will develop during the process, right? And that friction heat will helps you to stir and mix the material, right? And then you apply the another motion, which is called this motion. So till this point, right, there was only one motion, which is called rotary motion. And then by the time you finish this contact, there is another motion which would be given, which is called processing part, which is your transverse motion is given. And then you see the beautiful joint which has been pasted here, right, which would be created. And by the time you reach to end, you remove the tool, you will left with the small hole, right, which is just a replica of your pin, right, which is called exit hole. Now you see here, there is a small clip which has been given here for your own understanding. So whatever you have learned in the previous 2 slides, now you see there is a pin, right? There is a shoulder also. There are 2 aluminum plates you have, right? And you know, this tool is moving. This tool is moving, right, at certain RPM, 1000 RPM or 800 RPM, whatever may be the RPM. And you see this 2 aluminum plate has been supported with the strong backing. This backing is very important, which is stainless steel backing, right? You see there is a pin. So initially it is like a plunging, right? You see there is a plunging. So it is like similar to the drilling operation, but there is no material removal here. And that's the reason you have to do plunging very slowly. Now you see, after some time, your pin become invisible. After some time, your pin become invisible because pin has completely penetrated into the joint area, right? So you may have a question, what is that criteria? So pin length has to be lower than the plate thickness, 0.1 or 0.2 millimeter less than the plate thickness. Now you see, your pin become invisible. Now once the pin become invisible, right, as per the diagram, the next step is to apply the another motion, which is called feed motion, right? So feed has been given, right? Along with the rotary motion, the feed is been given on a vertical milling machine, and the joint formation, you can see, now you see there is no gap, right? And sometimes you can also tilt the tool also to 1 degree, 2 degree for a better consolidation of the material. Now you see here the tool is being tilted to about 1 degree or 2 degree. You see here. Now you see the joint formation has started at the back side, right? You see here. So this is how the friction stir welding works, right? So from here also, friction stir processing, which we would be discussing today, is based on friction stir welding only. So it is essential for us to understand friction stir welding and friction welding also. That's the reason. So friction stir welding has been derived, right, from friction welding. So first process is friction welding, second process is friction stir welding, right? And then from friction stir welding, there is a process called friction stir processing. So there is a, that is how the development has occurred. So now you see in this process, you can see there is no fume, there is no smoke, right? And you can understand that this process is green process. Why it is green? Because no fume, no smoke, no filler wire addition, no edge preparation, right? You are applying large amount of the downward force, right? And that downward, right? You see there is a strong backing which has to support that downward force also, right? So the tool which you are using, that is the heart of the entire process, right? It is non-consumable in nature. It is not going to consume. And you require a very good property when you are manufacturing the tool, right? So the tool material play a very important role. Tool material for aluminum and aluminum alloy, they are simple. H13 you can use directly. But then when you go to the high temperature material, like say you want to do friction stir welding of copper, right? Or if you want to do friction stir welding of steel and stainless steel. So you need to go with the high temperature tool material, like tungsten carbide with the rhenium, all those things are required. So this is how the friction stir welding works. And from here only, right? So you see there is a one fixture which you can see here, right? So you require a very strong fixture, right? Your backing is also required, fixturing is also required. You need to ensure that these two plates should remain in contact with each other, right? Because of downward force, the backing is required. And you need to ensure that these two plates should remain in contact. You require a stainless steel fixture also. You may have a question that why the stainless steel fixture is required or why stainless steel backing is required. Because stainless steel has a poor thermal conductivity, right? Stainless steel has a poor thermal conductivity compared to the carbon steel. And that's the reason, you want to retain that friction heat. And that's the reason stainless steel is more preferred for those applications. So hope you understood now this particular chart. You saw the clip also, right? That was our own clip. The friction welding clip was also our own, and friction stir welding was also our own. That was on a vertical milling machine. So FSW has number of attributes and can be used to develop a generic tool for the microstructure modification and manufacturing. And friction stir processing was developed based on this concept, right? So now you have seen the friction stir welding. Now friction stir processing. Now friction stir processing means what? Processing and welding. There is only one difference in terms of the term. You are doing friction stir welding earlier. Now you are doing friction stir processing. Processing means what? You are not joining the two metallic material, right? Instead of that, you take a single piece of plate, right? And just run your FSW tool. That becomes processing, right? It is as simple as. So friction stir processing, you normally, in welding, you normally weld two metallic material. Instead of that, you take just single plate and just pass your FSW tool, similarly what you did in the previous case, right? And when you cut the cross section, you realize that the microstructure in that process region is very different compared to your parent material. So friction stir processing is a variant of friction stir welding, right? And the focus not on joining of the metallic material rather than the processing or changing the properties of metallic material. Like you want to change the micro hardness, you want to refine the microstructure, you want to improve the hardness, right? With the same mechanism, with the same tool, right? So in the previous video, you saw there were two plates. Now you take just one plate and everything will be the same, plunging, then moving and stirring and mixing, all those things will be the same. So FSP has been applied to the wide range of material, because depending on the length of the pin, say for example, If you take a pin length, which is same as that of the plate thickness, it will be termed as a volume FSP because you are processing the entire thickness. But instead of that, if you take just 2 to 3 millimeter of the length of the pin, so then what will happen? You are processing only 2 to 3 millimeter layer from the top. So it is called surface FSP, right? Now, FSP to be readily applied for high melting point materials also, it is not that complex like FSW of titanium and nickel base alloy. And it is similar to your bead on plate FSW. A rotating pin or FSW tool is being plunged into the workpiece and transfers to the path region, and sometimes even raster pattern to produce a certain material modification over a desired area. So hope you understood friction stir processing, right? It is a variant of friction stir welding, and it is nothing but it's a modification wherein you are not joining the metallic material, but you are doing a material modification, or you are probably changing the metallurgical properties of the material under the stir region with the help of the tool, right? So let us understand in a more better perspective. Any questions so far? Do you have any question? Fine. So let us move to the to understand that now we have understood the basics of FSP. If you have a question, let me show you. You know how FSP and FSW is different. You see, you saw there are two plates you have, right? Instead of that, you take just single plate of 100 by 100, right? Or whatever, but there is no joint line here, right? And try to do similar what you have done in FSW, right? So then it's become FSP. That's as simple as. So FSP, now this simple modification, FSP and FSW, when you look at from a practical perspective, you realize that there is not much difference in FSP and FSW, right? Instead of joining, you are doing material modification, right? But this FSP has multiple applications, right? You can see there are many FSP tools or techniques which has been developed because of this friction stir processing, right? You can achieve superplasticity also. You can do casting modification also. You know, sometimes you end up with a lot of porosities in the casted components. So if you want to handle those porosities, you know, you can apply FSP tool and you can reduce those porosities in the aluminum castings as well. FSP can be used for surface composites also, which is what we are going to discuss today. Surface composites and superplasticity. And there are many other applications also like powder processing, channeling, right? So that's how there are, you can see a lot of applications which has been reported. So let's understand first, because there are 6 different 6 different applications which has been referred, which has been can be executed with the help of FSP. But we would be discussing 2 today: surface composite and superplasticity. Now, you see surface composite. There are 2 arrows you have, right? One is the mechanical mixing, and the one is the homogenization. This is what is the required. So you are adding certain reinforcement, right, in the aluminum matrix with the help of FSP tool. And the feature, you need to ensure that that powder should be uniformly mixed in the matrix of aluminum. That's the reason the homogenization is very, very important. That is what is the meaning of this feature. And then when you look at the superplasticity, you see, to get the superplasticity, the fine grain is the primary requirement, right? So we will be understanding these 2 applications in detail, right? Surface composite and superplasticity. So like compared to the your regular tool, what you have, right? You see here that you required a various kind of the parameters to control the properties, right? In FSW or FSP, you are required to control the rotational speed, the welding speed, tool tilt angle, plunge force, right? And the tool pin offset. All those things are very, very important they are equally important in FSW also. They are equally important in FSP also, right? And when you're working with the dissimilar material, there is one more feature which is important, which is the tool pin offset. So that is how. Now let's start with the first, which is called FSP for surface composite. Now you see, this is FSP for surface composite. Why there is a need to go with this FSP for surface composite? I'm sure that you can understand what do you mean by composite, or our interest. You know, there are a lot of composite materials you have, but there is one category which is called metal matrix composite, MMC, right? You have a polymer matrix composite also, right? You have a metal matrix composite also. You have a ceramic matrix composite also. So let's talk about metal matrix composite. So if you start manufacturing metal matrix composite, right? And you know, what do you mean by composite? you have the two material of completely different in nature in the same matrix, right? So what is the drawback of MMC? Drawback of MMC is what? Composites which are suffer from great loss in the ductility and toughness, right? Although they are very much light, right? But there is a major issue with the composite material is the loss in ductility and toughness when you are going with the MMC, right? So for certain application, the useful life of the component depends on their surface properties, such as wear resistance. So now it has been understood that when the material is under the application, right, it is assumed that most of the load which is being taken by the material from the surface of the material, rather. So they go with the development of surface composite rather than manufacturing the complete plate of metal matrix. So they go with the surface composite. Because of this reason, the great loss in ductility and toughness, they wanted to create a surface composite rather than the bulk composite. So under this situation, it is desirable that only surface layer of the component is reinforced by ceramic face. So you take a metallic aluminum plate and then, the surface of aluminum is been reinforced with the ceramic face, right? While in bulk of the composite. So what happened? It is like a sandwich structure. It is like a sandwich, at the top layer, because you have surface has been added with the ceramic. So that is how, and then the remaining core will remain as it is. Say you have a 6 millimeter aluminum plate. So top 2 to 3 layer is being reinforced by the ceramic, while the remaining 2 to 3 millimeter is the remaining original core. So, there is no loss of ductility and toughness. So inner core will have a ductility and toughness, while the top surface will give you very good wear resistance. And that is how these surface composites have come into the picture. Hope you have understood the logic why the surface composites are important. So then let's come to the technique. So we differentiate that what is the difference between composite and surface composite, why the surface composites are required. Now let's talk about the technology. How do you get the composite and how do you get the surface composite? So, you have the existing techniques like electron beam, you have laser beam, they are all, you have a stir casting method is also there, right? All those techniques you have, but they are all processing the material based on the liquid phase at high temperature. While, so when you have a reinforcement like ceramic phase, what you have, right? So it is very difficult to avoid the reaction between the base metal and the reinforcement. So there is a reaction between the reinforcement particle and the metal matrix, and which leads to the formation of certain detrimental phases, which are brittle in nature, right? And that's the reason. So, but if you process the ceramic into the aluminum with the solid state welding method, right, which are operated well below the melting point of the substrate, then you can avoid this problem, interfacial reaction. And that is how the friction stir processing comes into the picture. Hope you have understood the logic of this particular. So FSP is being used to create the surface composites, right? We are not going with the liquid phase methods. Why we have selected or why the researchers are selecting FSP method is just because it's a solid state and it is not going to create any kind of reaction between the reinforcement particle and the substrate, while it bound to happen with the. So there were two logic we understood, that why we are not going with the liquid phase method, why we are going with the FSP, and another thing which we discussed, why the surface composite, why not the bulk composite, right? So let's talk about the FSP. So when you are going with the manufacturing of surface composite using FSP, researchers have tried a lot of other reinforcement. You see here, there are a lot of reinforcement which has been referred here. And some of the reinforcement like boron carbide, silicon carbide, aluminum oxide, titanium carbide. These are some of the common reinforcements which has been added into the surface of the material. You can have substrate like aluminum, copper, right? Any kind of ferrous, non-ferrous substrates you have. And those substrates were inserted into the matrix with the help of FSP technique. How we will discuss. And among all these, boron carbide is being used widely because you see the density is very less, right? So it's become easy for you to stir and mix. If you look at the aluminum, right? The aluminum density is also 2.6, 2.7 grams per centimeter cube. So that's become stirring and mixing become easily. Now you see, how do you insert those composites, how do you insert those reinforcement which are mentioned in the previous slide? So you have a various methods. One method, you can create a hole. You see, there is an hole method here, right? And these holes, which are blind holes, they are filled with those ceramic particles, say boron carbide. Now this boron carbide, you mix with the acetone, right? And then you put inside those holes, right? They are blind holes. As I mentioned, you want to create a composite of 2 millimeter or 3 millimeter, right, from the top. If the plate is of 6 millimeter, you want just 2 to 3 millimeters. So then you drill a blind hole of those size, fill this cavity with the ceramic particles, which is in the form of slurry, right? So that it's dry powder, which is difficult to add into these blind holes. Then you close those channels. All the holes, they are open. So you take a tool, which you see, this tool is different. Now this tool doesn't have pin, right? Why you use this tool? Because you want to close the channel. All the holes which are open, you want to close it. So you close the channel, right? Then you take a tool which has a pin, right? So this pin, now you see, now on the same area, you are processing with the tool which has a pin, right? So that this powder which you added, which gets stirred and mixed with the matrix of the material. So there is a one method which is called hole method. Why it is called hole method? Because you are inserting that ceramic or reinforcement with the hole pattern, right? And then you are closing. So this pass which you are doing, which is called capping pass. Why it is called capping pass? Because you are closing the cavities, right? And then you take a tool which is your regular tool, right? This is your capping tool. This is your regular tool, and then which has been inserted, and it can be stirred and mixed, right? And you will get the matrix. Those ceramic particles get mixed into the matrix of aluminum. So this is one method, is a hole method. Another method, you can go with the groove also, because creating a hole and with the certain pattern, zigzag pattern, it's a time consuming process. And then instead of that, you create a slot or a groove, right, which is of 2 millimeter, 3 millimeter, 2 by 2 also. And then similarly, you fill this hole with the ceramic, right? And then the process in the similar way, the way you did it in the previous case. First, you go with the pinless tool, and then you go with the tool which has a pin. Now, you may have a question, what is the function of the pin? The function of the pin is to stir and mix the material, while the function of the shoulder is to generate the heat, right? Because shoulder cross section is 3 times the pin diameter, as I mentioned. And as the pin get inserted, right, it is going to help in your stirring and mixing of the material. It will help you to mix the boron carbide and the aluminum matrix in the thickness direction. So one method is a hole method, another method is a slot method to introduce the reinforcement into the matrix, and that too with the solid state rule. Now this process is friction stir processing for surface composite. You are adding to create surface composite. You can do plain FSP also. Plain FSP means what? Neither you create hole, neither you create slot, and nothing. You just take an FSW tool and change your microstructure under the shoulder region. Another method, which is called sandwich method also. Now, what is that sandwich method? Between the two metallic material, you put another layer, right? You put a layer, which is like this, right? And then you do stirring and mixing. So that's how you can create a surface composite, right? So you see, between the two aluminum plate, you have applied the layer of reinforcement, and then you run your, in that case, it is already closed. You don't require a capping tool, right? So you can apply your tool directly, and then you can process right, left, then entire area can be covered. Then the fourth method, which is a surface coating, wherein, you are just putting your layer only at the top, right? And then you paste your boron carbide or whatever, and then you run your tool side by side, and then you create a region of surface composite. So surface coating method, sandwich method, hole method, and groove method. So there are 4 major methods which are there for creating a surface composite using FSP2 technique. But these 2 methods, which is being widely used, hole method and slot method. Now, based on this, I'm going to give you some of the. Now, you may have a question that why there is a need to apply, because this pass which has been applied, which is called capping pass, and this pass which has been called is stirring pass. Now, capping pass and stirring pass has its own relevance and importance. What is that? Is it possible to apply this stirring pass directly here? No, you can't apply this. If you apply this stirring pass directly on this instead of this, then what will happen? Your powder will come out, right? And that's the reason it is essential that you first close the channels with the help of the pinless tool, and then powder will remain inside, and powder will distribute it, or its stirring and mixing become easy. Otherwise, what will happen? Your powder will come out.
हेलो सर,
Hello.
सॉरी फॉर इंटरप्ट। ये जो आपकी स्लाइड है वो फ्रीज हो गई है, अगर पॉसिबल है तो इसको रीशेप कीजिए।
अभी मूव हो रही?
नहीं हो रही है। 8 स्लाइड।
Now you are on which slide?
8।
8.
यस सर, फिर से शेयर कीजिए, उसको रीशेप करिए क्लोज करके।
8 स्लाइड पे है तो अभी तक कोई बोला नहीं कितनी देर से। So let me share once again. Now can you see?
Yes sir, it is okay.
Okay, so let me see 8 slides. So that means there are many participants. They are very much silent.
Yes.
They are not, because it indicates that we stopped this. The slides were freeze because of those technical issue. But then so
Yes.
this was the slide.
Yes,
Yeah.
right.
Yeah. Then did you saw the video also?
No sir.
That's a problem. No? That's a problem. Then I have already covered another 10-12 slides in between, but nobody has reacted. Now you
all
see.
are muted. Okay,
You
now
see there is a
all is
process
muted.
here. Now you see there is a tool. I am just running so that after some time the pin become invisible, and you see, and then you apply the feed, right? So you will get the joint in the solid state condition. Right. So this is what is the clip which was presented. And as I mentioned, that friction stir processing is nothing but it is not joining method, but it is processing, right? So there are various parameters you have, like friction stir welding. Whatever the parameters which are important in friction stir welding, they are equally important in friction stir processing also. Now I gave you the background of surface composite and the technique like liquid phase techniques and solid state technique. And there are various powders which can be ceramic phase, which can be reinforced, right? These are the some which has been mentioned here. And there are various techniques you have: hole method, slot method, sandwich method, surface coating method, right? There are various methods you have. In one method, you create a hole and you fill this cavity with the ceramic powder. In another method, you create a slot and fill with the ceramic. Then the second step is to process with the pinless tool. And the third step is to process with the tool which has a pin, so that the powder gets stirred and mixed. Similarly, you do in the groove method also. Then you have a sandwich method and the surface coating method. In both the techniques, you don't require a capping pass. You can apply your stirring pass directly. So let us come to the first case study, which is nothing but, you see how we are doing. So just, is the slide visible to you?
Yes sir, yes. Now
Okay. Now you see there is a small animation to help you out with the understanding that FSP for surface composite. You take a plate, and this plate, you see there are a lot of blind holes which has been created. They are blind holes. These blind holes now you fill with the ceramic powder. So I have filled those cavities with the ceramic powder. Then you process that area with the tool, which doesn't, you see there is no pin here. So you just close those channels, right? You close those channels so that when you apply a tool which has a pin, so that the powder should not come out from the cavity, right? That is what is the intention. So this is your first step, this is your second step, third step is to close the cavity, and the fourth step is to process with the help of a tool which has a pin, so that the ceramic particles, they get stirred and distributed. The function of the pin is to stir and mix the material, because now you have a two material. One is boron carbide, another one is your aluminum, right? So those stirring and mixing would be possible with the tool which has a pin. Now you see this is an actual photograph of hole pattern. You see there is a zigzag pattern you can see here, right? So then they are all blind holes, right? They are not through holes, right? And now you see those blind, you apply the reinforcement, which is your boron carbide, the paste which has been applied. Then you apply a capping pass so that you channel all the holes get closed. And then you apply stirring pass. The stirring pass will stir and distribute the boron carbide in the matrix of aluminum. So as I mentioned, that capping pass and stirring pass, they are very important. You can't apply stirring pass directly. If you apply stirring pass directly, then what will happen? There is a loss of powder, right? The powder will come out from the cavity because those cavities are open. But with the help of capping pass, you are closing those cavities and then you are applying the stirring pass. That's the reason. And you know, capping pass is just one, but you need to apply more number of stirring passes also. Why more number of stirring passes are required? Because then powder, you know, you need to ensure that the powder should be distributed more uniformly into the matrix of aluminum, right? So that the same area you need to stir 1 time, 2 times, 3 times, either same direction, either change in direction, right? So that powder will be distributed more uniformly. Now here, I'm just presenting a small case study to give you an idea about how friction stir processing was done. So this is plain FSP. Why it is called plain FSP? Because we have not added anything, no reinforcement, nothing. It is just plain FSP, just stirring. So we have applied only stirring passes. You see, we have taken one sample in which you have a 1 stirring pass, 2 stirring pass, 3 stirring pass. 4th sample where stirring pass directions were changed, starting become end starting. The sample was rotated at 180 degrees. Similarly, 3 stirring pass, but change in direction. You see, so single pass, there is no point in reversing because it's only 1 pass. So this is how plain FSP where no reinforcement was added. You see the photographs here, right? After plain FSP, no reinforcement, no hole, nothing stopped, right? Then the another method wherein we created the slot, right? And the slot of 2 by 2 was created, which has been filled with the boron carbide in the form of paste mixed with the acetone, right? And now you have a hole, or now you have a slot. So because of slot, you require a capping pass also, right? So similar experiment, but there is an additional capping pass you have. 1 capping, 2 capping, you see. So 1 stirring, 2 stirring, 3 stirring, right? Every time you have 1 capping, but all of them are in same direction. But when you have a 1 capping, 1 stirring, they are in opposite. 1 capping, 2 stirring, change in direction, and 1 capping, 3 stirring. So you may have a question that what is the reason for applying more number of stirring passes? The intentions are to ensure that those reinforcements should be distributed more uniformly into the matrix of material. So this is for the slot method because it is a slot, so you require a capping pass. Then the similar experiments were carried out with the hole method also. You create a hole, right, which is 2 by 2 deep, and then 1 pass, 2 pass, 3 pass, same direction, reverse direction. At the same time, there is a capping pass because there is a hole method. Is the slide visible to everyone?
Yes, sir. Screen is visible.
Okay, fine. So now you see these are now you see these are the photographs of the coupons which is being welded or processed, right? Single pass, double pass, triple pass, A, B, C, say, right? And then C, D, E. Yeah, so then you can see these are the actual photographs, right? Which has been processed. So then what we did, we then analyzed the wear behavior of 3 different case studies, right? You know, I mentioned to you the plain FSP where there was no reinforcement, 1 pass, 2 pass, 3 pass, same direction, 2 pass reverse direction, 3 pass reverse. Then, you know, there was a hole method, there was a slot method, then there was a hole method, right? The red one corresponding to the hole method. The green one is corresponding to the slot method. And you see the FSP regions also, there was no reinforcement. And this is your parent metal wear, right? So wear volume in terms of millimeter cube, right? You see the parent metal wear is very high, close to 5.41, right? And if you just process it, right, without any addition of reinforcement, you see there is a drastic, because that indicates there is a good amount of the refinement in the microstructure and the precipitates also. And when you have hole method and slot method with the reinforcement like boron carbide, you see there is a further reduction in the wear, right? So that indicates that there is a greater improvement in the wear resistance, right? With the addition of, and if you see the red are the best one compared to all of them because it's a hole method. Hole gives you more uniform distribution of the reinforcement into the matrix compared to the slot method. The slot, you know, you are already putting all the material at the one go, while in the physically in hole method, they are already distributed at different location. So the distribution into the matrix is very good. And that's the reason you can see here, you can see all those white particles. They are nothing but 1 capping plus 3 stirring, but into the opposite direction. So this indicates, you see, these are all, that was an optical picture. This is your scanning electron micrograph. You see that these are all boron carbide particles which are distributed uniformly into the matrix of aluminum. And you know, you started original size of the powder particle, and that also get reduced and fragmented during the process, right? You see, this indicates the uniform distribution. So that was one case study which indicates that, you know, what is the outcome of this study? We found that the surface composite produced with the FSP significantly higher wear resistance over the base metal, 87%, right? When you compare this value with the, you see what you are getting is, say for example, maximum is 0.95, and when you compare with 5.4, right? So which is around 87% reduction in the wear, right? Even the specimen, when you process with the FSP without any addition, you just do plain FSP, you don't add anything, right? This one, in that case also, the wear, there is a 56% reduction in the wear, right? And we found that this 1 or 2 passes, and that to reversing direction, right? Instead of applying all the stirring passes in the same direction, if you change the direction, right, this will help you for a better distribution. This is what you can see here, right? Your reinforcement has been distributed more significantly rather than agglomeration. One of the limitation of the process is to avoid the agglomeration. If the particles, they get agglomerated at one location, right, you will lose the property. So particle has to be distributed more uniformly. And how you will ensure more uniform distribution of those reinforcement? With the help of more number of FSP passes, either in the same direction, either in the reverse direction. So these are some of the publications of the work done by the, so one of the PhD candidate, Dr. Kunal Mehta, he worked on this area and he published 2 journal papers, and there are 2 conference papers in the prestigious journals as well. So that was about the case study 1. Now let's look at the another case study, which is on hybrid surface composite, right? Friction stir processing only, but you know, you are creating a hybrid composite instead of mono. You know, earlier you used to add only one reinforcement, which is your B4C. Now you are adding additional reinforcement, right? There are 2 different types of the powders you have. One, which is your boron carbide, another one which acts as a lubricant. Now let us look at that as well. So here in this particular case study, what has been done? You see here, you have in same aluminum, you are mixing 2 different powder. One is boron carbide, which we just studied, and another one is MOS2. You may have a question that why there is a need to add 2 different. This boron carbide act as a reinforcement, and while MOS2 act as a lubricant. So there are few reports which indicates that addition of MOS2 or any lubricant will help you to improve the wear resistance even further back, right? So what we have done a systematic study with the hybrid surface composite as well, and we optimize the mechanical wear properties as well. So these are some of the SCM pictures of boron carbide and molybdenum disulfide. Molybdenum disulfide is normally being used as a lubricant, right, in the dyes. So here you see there are 2 different powders we have selected. One is the boron carbide. You know, in the earlier case, we used to add only the boron carbide. Now we are adding boron carbide plus MOS2 with the certain proportion. So here there is a systematic study which was done in which 100% B4C to 100% MOS2, and with the ratio of 25, 50, 75. That was the ratio which was varied, and the experiments were conducted with the help of Hole method. You please understand. Now, whatever the parameters were optimized in the previous case, right? In the case study 1, what we found in the previous study, we found that the 3 passes, but change in direction was the best, and the Hole method was also best. So we consider that as a condition, right? Now we didn't vary the Hole method, slot method without FSP. We just started with one particular system, which is your Hole method, which has the best wear resistance, and the 3 passes with the change in direction. And then all these compositions, starting from 100% B4C to 100% MOS2 were tried, right? You see, this is your 3 passes, right? A coupon, B, C, D. You see, your A was the 100% B4C. B, C. Then, as you are approaching, because your MOS2 percentage is increasing, you see here only 100% B4C, while here you see 100% MOS2. You see, because MOS2 is dilubricant. Now it is acting as a lubricant. Now beyond 50%, you see here, this is C is your 50-50. This is your C, which is 50-50. Now, the moment you cross 50%, you see 75 MOS2. It is very difficult to get a good quality joint, right? And then 100% also, because you are giving more lubrication effect, right? You are giving more lubricating effect. That's the reason this MOS2 has been up to 50% is advisable. Beyond that, you see lubrication effect is very high, because for frictional processing, you require certain friction, right? Because of that, lubricant, the friction is not happening. And this is without any addition for the comparison purpose. And those were characterized with the wear behavior as well. And you see the optical microscopy was done, and then it confirms the presence of MOS2, and it also confirms the presence of B4C in the matrix of aluminum. And after going for this wear behavior, we found that this particular, which has the 25% MOS2, has very good wear resistance, and that was subsequently help us to characterize the wear behavior. So that motivates us to do further reduction, because when we did the wear testing, we found that the 25%, yeah, let me show you, yeah, you see here the wear behavior here. You see the blue indicates the wear in volume loss. You see, this is your base metal. Then you do FSP, which is 53 passes without any addition. You see the 100% B4C. There is a drastic loss in the wear, right? And then you see, if you add instead of 50%, you see here, you have a 12.5% MOS2, which has the least wear, which is very good, right? Whole method and slot method. But the moment you have 25% MOS2, you see the wear has further increased. 50-50 has the highest. So what we found that the 12.5% MOS2 is the best composition, or whether it is a whole method or a slot method. Whole is more preferred because it has the least compared to the groove, minor difference. So we found that among all the compositions which has been varied, we found that, then we did the hardness measurements across the stir regions for all the compositions from 100% B4C, right? And you see, we found that this is your red one, which is your FS speed. And you realize that the 100% B4C has the highest hardness, right? But if you compare with this 12.5% MOS2, which is your which has lower hardness. So that also confirms that all hybrid composite display a lower hardness than the B4C mono composite. Moreover, the hybrid composites reveal the reduction in the trend with the increase in MOS2 fraction. As the MOS2 fraction increases, you see there is a yellow one. You see the yellow one, which has a 50%, which has the least, right? So that is how the hardness trend is there. And this trend is also longitudinal also, and the vertical also. You see here also that hardness measurements were carried out not only in the transverse direction, but within the stir region also, from top to the bottom. So this also indicates that once you have the highest percentage of MOS2, which has the least hardness, and the green one is the indication of 100% B4C. And those trends are also matching with the wear behavior. So wear resistance in agreement with the hardness data of FS speed samples and the base metal, and hybrid composites with the MOS2 fraction showed a poor wear resistance due to more lubricant and less abrasive particles, similar to the hardness. So among this study, the best is this particular combination, which is 12.5% MOS2, is the one which gives you the least wear resistance. Even if you compare with the 100% B4C, in the previous study, you were getting like this, but when you are adding hybrid, right, you are further reducing, right? You are improving the wear resistance like anything. And these are some of the micrograph SCM images of those surfaces, which indicates that you have both the type of adhesion and abrasion kind of the wear, which has been presented in those SCM micrograph. So this is another slide which gives you an idea about the coefficient of friction under the different compositions, right? Starting from 100% B4C to the all plain FS speed also, and as received 6061 also. So the major output of this study is that this B4C hybridization composition is the best, that too with the 12.5% MOS2, which is the excellent. And these are the some of the paper which has been published by the Dr. Sharma. He was the PhD scholar, and he worked with the PDEU for his PhD, and he has published 3 good quality journal papers, 2 under Journal of Tribology, 1 is under the Material Science and Engineering Technology. So that was the B4C. So we understood 2 case study, one which was related with the normal, another one which was the hybrid, and this is now 3rd case study, which is friction surfacing. Friction surfacing is another technique to, so now we talked about friction welding, then friction stir welding, then friction stir processing for surface composite. And there we talked about 2 case study, right? Now the 4th technique is surfacing. You see here, there is a diagram in front of you. So there is a tool here, right, which is a consumable in nature, right? Let me show you the clip here for a better understanding. Now you see here. So your rod which you have, which is a consumable in nature, right? And it is consumed during the process. You see, initially it is like a pencil tip, and which is forced towards the substrate. And between the rod and the base, there is a viscoplastic layer, right, which has been deposited. Now this layer, what you are feeding now, you know, if you introduce those hard particles in the consumable rod itself, right, you see, you try to visualize there is a central, there is a hollow cavity, and this cavity is filled with the boron carbide particle. Then those boron carbide particles will become part of this deposited layer. So friction surfacing is a technique which is called solid state cladding, wherein also the wear behavior of the surface layer can be improved with the help of those reinforcement particles. So here you can see here there is a small clip. This is again our own video. You see here there is an aluminum layer which has been created, right? So this aluminum layer, you see there is an aluminum rod which is tilted to 2 to 3 degree, and you see the layer, right? And here you have around 2000 is the RPM, right? And diameter of the rod you can see, right? And the temperature measurements are carried out on advancing side and the retreating side, right? So you can see the layer, aluminum layer, which has been deposited here, right? So this is called friction surfacing. So what we have done in our lab, we deposited 1 layer of aluminum, 2 layer of aluminum, 3 layer of aluminum. But in this single layer, what we have done, we have introduced the boron carbide particles, right, through the aluminum rod. You saw there was a video, right? So the central, we created a drill, we created a blind hole, right? And then we filled that cavity with the boron carbide slurry. And then we started the friction stir processing, friction stir surfacing, and those boron carbides become part of the layer. And then we did the wear testing also with the single layer, double layer, with the boron carbide layer also. And we found that you see those boron carbides particles in the aluminum layer which has been deposited. You see the wear behavior of the normal single layer, which is close to around 138 micron, and here which is close to around 105 micron. So there is a drastic reduction in the wear in terms of micron, right? So wear resistance increasing by 13 and 24% with adding B4C particles, right, at 20 Newton and 40 Newton respectively. So these are the 2 different curves. They are corresponding to the 40 Newton, right? But you can see around 13 to 24% improvement in the wear behavior. So that was about the friction stir processing and friction surfacing for surface composite. Now there is another element which is called superplasticity. Now friction stir processing, you know, I told you that basic FSP is what? You don't do anything, you don't add anything, and just you process the material. Now what happened? You, instead of 2 plate, you just take single plate, right? And allow your tool to follow the same principle as that of FSW. So what happened? So when you process that region, right? And if you generate a tensile specimen from that region, from the stir region, this is your original specimen, right? You please follow the cursor. And then that specimen is subjected to tensile loading, right? But at high temperature. So you realize that the material is displaying elongation, which is more than 200%, right? You see in this case, it is 1050. So in that case, you can say the material is superplastic, right? The material has the superplastic behavior. Now, why you are getting that superplastic behavior? Because with the help of FSW tool, right, you have done the processing in that region. And because of that processing, you know, there is an extreme grain refinement you have. You have a very good uniform grain structures you have. At the same time, you have those precipitates you had earlier in the parent metal. They were also fragmented and distributed more uniformly into the matrix. And because of that stirring and mixing, you know, you have a large amount of the high angle grain boundaries. If you can, these are all the things which you are achieving while doing friction stir processing, right? Please understand, we are talking about plain FSP. We are not talking about anything that we are adding any reinforcement. When you take a tool, and if that tool is just run through the aluminum plate, right? If you are, depending on your process parameters, you may get fine grain structure, you may get equiax grain shape, you may get very fine second phase particles, large angle of grain boundary. These are the attributes which are required to get uniform elongation, right? If the elongation is more than 200%, material is being considered as a material has the superplasticity. So that is also achieved with the help of FSW tool. So as I mentioned, the FSP is being used for casting also. You know, in the casting, you have a lot of porosities. Those porosities also can be handled. You have those porosities at selective locations. So if you want to remove those porosities, right, you can use FSP tool to remove those porosities and the performance can be enhanced. So aluminum casting contain those porosities, segregations, chemical compounds, inhomogeneous microstructures, which can be contributed to the property degradation. So FSP tool can be used for even for castings. Now, you may have a question that how you are getting a very good elongation, right? And what is the use of having this high elongation? So when you have the, you know, aluminum, there are various kinds of the aluminums you have. Precipitation hardenable aluminum you have, like say 6000 series, 7000 series, 2000 series, right? So those precipitates, what you have, right? These precipitates, right? They are less capable to deform because they are not going to deform much. They are less capable of plastic deformation than the matrix. Aluminum is going to deform more rather than the precipitates what you have. And because of that, you know, there is a possibility of cavity nucleation, which is very frequent. You may get the cavity, right? Because you have a two different material, like one is precipitate and another one is the matrix, and both are deformed at the same parameters. So because of difference in the deformation trend, you may get the cavities. And FSP allowed to break off these large precipitates and disperse in the home. Because of this friction stir processing, those precipitates, you know, they also get fragmented and they also distributed very uniformly into the matrix, into the material. That is one of the reasons that those precipitates also restrict the dislocation movement, and you will get very good elongation even at the. So one particular reason is the precipitate. Another reason is the grain refinement, because precipitates are also deforming and reducing their size, and the matrix, right? Whatever the matrix you have, that also refines during the process because you are doing friction stir processing. So FSP generate the fine microstructures and equiax grains, right? Which leads to either an increase in a strain rate or decrease in the temperature at which the superplasticity is achieved. So you are doing superplasticity test. Now if you are getting a superplastic behavior at very high temperature, which is not advantageous compared for a commercial application. But if you are getting a superplasticity at the lower temperature, which is more advisable from an industrial perspective, and the rate at which you are getting strain rate, right? If that is slow, then it will take a long time. So lower is the strain rate, more time it will take. So higher strain rate and the low temperature is the one which has been more preferred from superplasticity from a commercial angle. And the grain refinement induced dynamic recrystallization. then the nugget contributes to increase in hardness. So this is another mechanism, the grain refinement and the precipitates distribution. So mechanical properties such as even ductile, fatigue, formability, those things are also get enhanced with the help of FSP, right? Why? Because those large amount of precipitates what you have in the matrix, right? They also get deformed, they reduce their size, and they act as a barrier to the dislocation motions. And you have a uniform equiax fine grain structures, right? Which also helps you to enhance the superplastic behavior of the material. Now, just to give you a few more glimpse of FSP, friction stir processing, you know, as I mentioned in the beginning, you have a two type of FSP, volume FSP and surface FSP. If your pin is penetrating throughout the thickness, it is called volume FSP. If your pin is penetrating only to 2 to 3 millimeter, it is called surface FSP. So depending on your requirement, you can do volume FSP also, you can do surface FSP also. You see here, this is a base metal and you have done the surface FSP, only 2 to 3 millimeter. And then you have done the volume FSP, right? If you do volume FSP, the entire thickness has been processed. You see the ductility which has been bent angle through the bend test which has been shown. Similarly, here also for 5000 series, you see the surface FSP and the volume FSP. So you are improving the material's property, right? Through the mechanism which I explained to you just now. So with this, I have come to an end of my talk. But before I end the talk, I would like to show you some of the welding research facility available at Petroleum University. And just to give you the glimpse, so we have a dedicated friction stir welding facility for processing surface composite friction stir welding also, all in one solid state unit. This is another setup which we have, which has been created under the ISRO project for friction stir welding, dedicated machine available for friction stir welding, friction stir processing, friction stir superplasticity, right? All those things can be done on one machine. Then we have another machine which is called friction stir welding only, but that is for dissimilar metal joining and for friction surfacing also with the load cell and the variable RPM and the variable feed speed. Then we normally, you know, friction stir welding can be with assisted heating also. So TIG welding and friction stir welding can be combined together. So that is also available in our lab. So this is hybrid setup which we have. The recent addition into our lab, which is your hot wire TIG welding setup, right? You have a hot wire TIG welding power source, and there is an extra heating unit for heating of the filler metal, and which has been supported with the trolley to move the torch in XYZ direction under the BRNS project. Then we have a ultrasonic welding facility also for metals and plastics, right? So this is for metal, right? This is for plastic. So we have both the machines available, right? And we are doing research in that direction as well. So as I mentioned that we have a characterization facility for wear testing. Yeah, pin on disc wear testing we have, right? So it can be used for 4 different modes, dry condition, wet condition, pin heating, and furnace heating also. As I mentioned about the hot tensile testing for superplastic. So this wear testing has been used for those surface composite characterization, and the superplasticity for hot tensile testing. We have a dedicated hot tensile testing unit. You see the machine with the hot chamber, computer control, right? And the temperature measurements. So with this, these are the certain references which I have used in the presentation. I'm thankful to all funding agencies and all past and the current PhD students, because this work is nothing but carried out by them. So with this, I have come to an end of this presentation. I would like to thank you all for your patient hearing. And I also would like to tell you about IIW India. We have the professional body Indian Institute of Welding, right? And they are for promotion of welding science and technology. You may please visit the website of iiwindia.com. And if you wish to become a member of this professional body, you please feel free to contact me. With this, I have come to an end of this presentation. Thank you once again. Your questions, please.
Any participant want to ask the question to sir? We have given rights to unmute yourself. You can unmute by yourself and you can ask the question.
Any question?
You can reply the questions. If it is not possible to ask a question verbally, you can also mention it in the chat box.
I think there are many faculty members are attending this particular faculty development program. And, so because if you have any specific question, you may please ask.
Hello.
Yeah.
Hello, sir. Yeah,
Please.
sir, I want to know what is the basic difference between friction stir processing and friction surfacing.
Okay, so friction stir, let me take you, in friction stir processing, you have a tool which is non-consumable in nature, right? And while in friction stir surfacing, you have a tool which is consumable in nature. You see, there is a tool, right, which is in the form of rod, which is getting consumed, and you are creating a layer here, right? So this is friction surfacing. But in friction stir welding or friction stir processing, you have a tool which is non-consumable. It is not going to consume the way you see in this video, right? And this rod, it is consumable. You create a hole and powder reinforcement can be added in the center of the rod, and then that become part of this deposited layer as well. Is this clear?
Yes, sir. Thank you, sir. It is clear.
Sir,
Okay.
sir,
Yeah, go ahead.
regarding cutting to these stir welding tools, what are the materials that are used for making of these tools?
Tool materials, say for example, if you want to work with the aluminum, right? You can use H13. Tool steel.
Tool steel.
Yeah, tool steel. H13 is the best for aluminum and its alloy. But if you want to work with the copper, you need to go with the tungsten carbide.
Tungsten. Okay.
Yeah, and if you want to go with the stainless steel, you may require another high temperature material.
Sir, is it varied for the thickness of the workpiece materials, the cutting to diameters?
Yes. Correct. You are right. If my job dimensions are different, right? Then I need to design a different tool.
Sir, is it available in the market, or should we make our own tool?
No, we have to design our own tool based on our based on our base metal and base metal type and its thickness.
Okay, sir. Thank you, sir.
Any other question?
There are no questions, and we can conclude this session.
Fine. So if you wish to get more information about PDPU, you may please visit the website of PDPU. We do have a skill development program. The announcement of the skill development program is also available on the web page, right? pdpu.ac.in. And if you have any specific question, please feel free to contact me. My email address is also given here. Thank you.
Thank you very much. Thank you, sir, Vishwesh Badheka, for the session. We hope that content of the session will be helpful for our participants.
Fine. So, anything more I need to do?
No, sir, you can leave the session.
Okay, fine. Thank you very much, and we'll have another session tomorrow morning, right?
Yes, sir.
Okay, fine. I request all the participants that whatever the things which we have learned about friction stir welding would be equally useful to you in the second session, which is scheduled tomorrow morning, 10 to 12.
Okay, sir. Thank you.
Yeah, thank
you. Common instructions, as I have repeated in the first session. The feedback link is sent in the chat box of session 2, and all the participants have to fill that feedback of the session 2nd. Now, session 3rd will start at 2:30 p.m. So it's request to all the participants to join before 5 minutes. The link is sent in the chat box for the feedback of the session 2. And I will meet at 2:30 p.m. Thank you very much.